And now my other computer's going into lock.
Oh. That was awful.
Can you turn your camera off, please?
Me?
Yeah.
Me, Callum?
No, Pete.
Oh, okay. Why is that? Because he's eating.
No, he's just jealous because I'm muted.
See, right down his throat. That was horrible.
Right. Are you listening? Now we need to introduce the fact that VS is equal to 10 over S. So what then we can do is start to write our expression for I. S. It is 10 divided by S divided by ZS, which is this. Hang on, we probably better to do a little bit more here first.
Mike, with your VS on there,
Yeah.
will that always be your voltage over S then?
Yeah, if it's a step, Kieran. If you look at your table of transforms,
Yeah.
the step input is the voltage divided by S. Yeah.
Yeah.
We need to multiply out these terms in here. So 10 times 0.01 S is equal to 0.1 S. Yeah. Plus 0.4 S times 0.01 S is 0.04 S squared. And then the end is just 1. And all of that is over 0.01 S. Now we can bring in the fact that VS is equal to 10 over S.
Have we lost? Oh no, he's unfortunately still there.
IS is equal to VS over ZS, which is 10 divided by S on the top of the fraction, and then all of this bit underneath 0.1 S plus 0.04 S plus 1 all over 0.01 S. Everybody follow that so far?
Yeah.
Yeah.
So we've got an expression now that is a fraction divided by a fraction, so we have to deal with that.
How you getting on being a system tech, Callum?
Badly.
Right, so we got that on this. Guys, that can come later, please. Right, so we put 10 over S here, and then we multiply that by the other fraction turned up the other way. So let's multiply in there. 0.01 S divided by 0.1 S plus 0.04 S plus 1. Yep. Everybody happy with that?
Yeah.
Yeah.
And then if we multiply the top and bottom out, so 10 times 0.01
Sorry, Mike,
S.
was that not 0.04 S squared? Did you not mention before?
Yes, it is squared, Peter. Well spotted. You spotted my deliberate mistake.
Yeah.
Yep. Okay.
Cool.
Okay, then, so what we've got is 10 times 0.01 S is equal to 0.1s. Yeah. Divided by, and then we got s times 0.1s is 0.1s squared. Hang on, I know what we need to do. We write that like this. S times 0.1s plus 0.04 s squared plus 1, all multiplied by s. What you can then should see is, what can we do?
No need to expand it, is there?
No, what?
Oh no,
what,
would you
what,
get rid of common ones?
You've got
No.
s divided by s here. Hang on, let me undo that. You've got s on the bottom and s on the top. Yeah. So
Yeah.
they cancel out.
Yeah.
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 So we got this 0.1s, 0.1 over 0.1. That's a 1, not 2. (0.1s) plus 0.4s. So effectively we've got this. I'm going to write it out again. 0.1 divided by 0.1s plus 0.04 s squared plus 1. All happy with that so far?
Mm-hmm.
Yeah. Now what we want is we're going to divide by 0.04. Get s squared on its own. Yep. So if you divide 0.1 by 0.04, you get 2.5. And then this becomes 2.5s. This becomes just s squared, which is what we're looking for. And the constant on the end becomes 25. Yeah. And always remembering that's is equals that. Yeah.
Mm-hmm.
Did you weren't here last? Who else? Who was here last week?
Oh,
Yeah.
I wasn't here.
Because it was
Sorry?
his birthday and he was being Bender.
Just you, Dan, wasn't it?
Yeah,
He
my
turned
missus
40
had planned
last week.
a day
What?
for my birthday, so I couldn't really. She was a bit annoyed with me, so I couldn't really get out of it.
No, all I'm wondering is, did you look back at what we did last week?
I haven't seen it. No.
No. Okay.
But I will start. I'll have a look
Because
this week. on the
you
day off.
absolutely, you might get a little lost in the next bit I'm going to do because you weren't here last week.
Yeah. Yeah, that's
Right.
fair enough. Yeah.
What we're looking to head for, we should remember, there's an expression that looks like this form. I omega over s plus b all squared plus omega squared. Yeah.
Is that an A?
That's what we're.
Say? A omega.
That's I omega, yeah. And the reason for that is that transforms back to an expression that is I e to the minus bt sine omega t, which is a damped sine wave. Yeah. So if we can get our expression to look like this one, with a constant and s added together and all squared inside brackets, a constant squared on the end representing omega squared, and another constant on top representing I times omega, the two omegas being the same. Yeah.
Sorry,
Okay.
Mike, what does that bottom say? What does it say again? After
This
the
bit down
minus
here,
t? Yeah.
that's minus b times
Yeah.
t,
Yeah.
all multiplied by the sine of omega
Oh,
t.
okay. Yeah, it says sine. Yeah, I'm with you.
Yeah. Okay.
Yeah, I'm good.
So we've got a constant here. We've got a constant here. But we haven't got this s plus b squared. We haven't got this perfect square bit here, the perfect square plus a remainder. Those of you that were here last week will remember that. So we need to get this quadratic down the bottom into perfect square plus a remainder form. Yep. And the way we do that is we know that, let's start to write it out. So we're going to say it equals 2.5 on the top. We want s plus some other number, all squared, plus another number. Yeah? Because when you multiply out that, you'd end up with your s squared. So we need to half this 2.5, because then, which is 1.25. Just showing you where that comes from. That means if we multiply out s plus 1.25 by s plus 1.25, we get no, that's not right, is it? S times s is s squared. S times 1.25 is 1.25s. And S1 times 1.25 is another 1.25s. Yeah. Times 1.25 plus 1.25 squared. I don't know what that is at the moment. Yeah. But what I'm saying here is, this is where this 1.25 comes from, because then when we multiply it back out, we end up with 2.5s again. Do you all get that?
Mm-hmm.
Yeah. So the efforts to get this into perfect square form involve us halving the coefficient in front of the s term. So we put the set of brackets in, we write s on the left, we put plus, and then we half this coefficient here, 2.5, and we put that in there as well. And then the remainder is, so this remainder on the end here is equal to 25 minus the 1.25 squared that we get from multiplying those brackets out. Yep.
Mm-hmm.
And that comes to 25 minus 1.25 squared is 23.44. Yep. So we've taken that 25 constant there, this 25. Yeah. And we've taken 1.25 squared off it because that's dealt with the square on a 1.25 here. And that leaves the remainder 23.44. All happy with that?
Yeah.
Yeah, I think so.
So, next thing to do is we can say this bit is omega squared. Omega squared is equal to 23.44. Yeah. Therefore, omega is equal to the square root of 23.44, and that equals 4.841. Yeah. All right. Then what we can do, this bit on the top here, if we look at our B, we know is equal to 1.25. And we know that I times omega, this 2.5 here, is I times omega. So I times omega equals 2.5. Therefore, I is equal to 2.5 over omega, which is 2.5 over 4.841. Just bung that in your calculator, please, and give me an answer. Got me an answer, anyone?
Is it 4.841 at the end there?
Yeah, 2.5 divided by 4.841, yeah.
0.52 or
Give me another.
0.516.
Allow that. .516. Yeah.
Mm-hmm.
So that's A. So now we've got everything we need to use this transfer and back down here, because we've got it in this A, we know omega, we know B, and we know omega squared. So we can say I t is equal to I, which is 0.516, E to the minus B, 1.25 t, yeah, times the sine of omega, which is 4.841 t.
That time sign, did you say?
That's a times in there, yeah.
Yeah.
All right. So that's our expression for the current in that circuit in that transient period after switch on.
Yeah.
Okay. And the type of graph, when you now start having a look at the problem I've given you, the first one in the handout, I'll get this up on Desmos so you can see it. But what you've got there, if you graph that, you'll get a damp sine wave that goes like so.
Mm-hmm.
I mean, in actual fact, if you get the component values right, you can get that perfectly damped. But this is what you would generally get, that where this is the exponential part, the first part of the expression, and then this is your sine wave, so it becomes a damp sine wave. All okay with that?
Yeah.
Mm-hmm.
Yeah. So in your handouts that I've given you for today, you've got the Laplace summary problems. And the first one, excuse me, step input of 50 volts into an inductor of resistance 0.5 and inductance 200 millihenries in series with a 500 microfarad capacitor. So that's a problem that is similar, as a step into series RLC, like we've just done. So start having a go at that problem. I'll graph this one on in Desmos so you can actually see what it looks like. Yeah?
Yeah.
So what have you started with? What's your expression for ZS?
Oh no. Right, well, my expression to start with was ZS equals 5 plus 0.2S plus 1 over
Where'd 5 come from?
Yeah, where are you getting 5, you bender?
5 ohms.
It's 0.5, you piece.
0.5.
No, it isn't.
Yes, it is.
Look at the question, Callum. 0.5.
Oh,
So that's where you
right.
fell at the absolute very first hurdle.
No, I didn't. No, the very first hurdle was 50 volts.
No, the very first hurdle was reading the fucking question.
50 volts was the first hurdle.
50 volts you got, yeah?
I've got that, so I'll claim that as a success.
Inductor of resistance 0.5 ohms.
Have I got this right?
An inductor of resistance. So there's 2 inductors.
No.
Oh,
The inductor has a resistance of 0.5 ohms and an inductance of 200 millihenries. So these 2 components here make up the inductance. It has resistance and it has inductance. So you should have 0.2S.
You're not screen sharing, Mike, I don't think.
No, I'm not, am I? Hang on.
I think I might have to have another pack of Watsits.
Yeah. Okay. Right. Callum.
Yeah, I've got that
The
wrong.
question says, yeah, so it's 0.5 plus 0.2S plus 1 over 0.305S.
Yeah,
Yeah.
I got.
That's what you got, Peter, yeah?
So where did I go
And
wrong
then-
with the divide by 0.02? Is that not right?
Where,
we'll
where are you up to? Yeah, you
I
tell
got
me
to
when
the-
we get to that.
Okay.
All right. So then we want to write that as one fraction with a common denominator. Yeah. So we've got to multiply everything by, except this time by 5S. Yeah. So what you should end up with is all over 0.305S, and up here, once you've multiplied it out, this is
0.5.
0.3025S
Oh, what?
plus 0.301S
Oh, okay.
squared.
Oh, you bender. Cock. Yeah, I'd see what I've done here.
I've not put the intermediate step in, but it's in the +1 on the end there. Yeah.
Yeah.
Okay. Then we bring in the current expression being 50 over S divided by all of this bit. I'm going to cheat.
Let's see. Divide by 0.0001.
Yep. All happy with that? And then we've got to the bit where we want to multiply out. So we have 50 over s. We're going to multiply that by the other fraction turned up the other way. So we've got 0.0005 s on the top, 0.0025 s on the bottom, plus 0.301 s squared, plus 1. Yep, you all get that far. Notwithstanding that someone started off with 5 ohms instead of 0.5.
I'll tell you something else I've done as well. Made another mistake. I've
Yeah.
mistook your classic. You did actually say this at the start of the unit, Mike. I've actually mistook 0.2 for 0.25.
Oh, okay.
So I've ended up with 0.000125 as opposed to 0.001.
Well, you know, we all make mistakes. Learn from them.
I'm
Copy.
going to give myself a good beating in a minute.
I bet you will, you dirty bastard.
Paste that on a new page. So, guys, that'll do. Come on. On the top line multiplies out. So we do 50 times the 0.0005 s. That comes out as 0.025. No need to multiply it by the s because that's going to cancel in a minute anyway, because when we multiply this bottom line here by s, 2 s's cancel out anyway. Do you remember that?
Yeah.
Or do you want me to write it in? Yeah, you remember that, yeah?
That one, yeah.
So 0.0025 s plus 0.0001 s squared plus 1. Yeah, because the s top and bottom cancel out. Okay?
Yeah.
Yeah.
And then we're going to divide by 0.301 to get s squared on its own. Yeah. When you do that, you should get 250 on the top. Did you get this far, guys?
No.
This is where
No.
I will do next.
I got to this point, I've got to times the 50 bit, so I carried on and I divided 0.005 and everything else by 0.001, so I messed up.
Yeah, you've got to divide every term by it. So you end up with 2.5 s here.
Plus s squared plus 10,000.
Plus s squared. Yeah. Plus 10,000. Correct.
Yeah, so I got the bottom line right, but I didn't get the 250. I got 5 for that because I forgot to times the other one by 50.
Oh, well, oh, you didn't at this stage up here.
Yeah.
You multiplied the top by 50.
No. So I carried on with a 0.0005.
Oh, okay. You'll learn by that mistake then, won't you?
Yeah.
Yep. Okay. So what have we got to do next?
Is it the A omega over SB stuff?
That term we've just put down represents IS, yeah?
Yeah.
Yeah.
Yes.
Now do you have to find the abbreviation for the function?
We've got to write this bottom line as the perfect square, haven't we?
Ah, right, yeah.
Yeah. We need to make this in s plus b squared form. Yeah, with a remainder.
Oh, okay,
So we
yeah.
keep the 250 on top. We start our brackets and we put s in. then we've got a remainder here. Yeah. And this number that goes beside the S here is, remember, is this 2.5 halved.
1.25.
So that's 1.25, and that's got to be squared. Yeah. And this bit is 10,000 minus the 1.25 squared. Yeah. You should get 250 over S plus 1.25 all squared. That's your perfect square bit. And your remainder is 19998.44. Shouldn't round that too much at that stage, because remember, you're going to take the square root of it in a minute to find.
You've added one too many nines.
Have I?
Yeah, it's not. You put 19,998. Not.
That is 19,998.
Is it? How come my calculator's worked out?
Oh, hang on.
It's 10. No, it's 10,000 minus. Yeah.
Yeah,
you've written it as 20.
Yeah, I've got a mistake in my solution. Sorry, that's my fault. So that should be 9,000. That one has got to come off the front, isn't it?
Yeah, 9,998.4 I got.
Yeah.
Your age.
I'll put that solution right, guys. I'll put that solution right before I give it to you. All right.
Yeah.
So I got the wrong bloody.
Hello. What doing?
What doing?
What?
Someone's got their dog out.
He's been out in his kennel. He just comes in every so often to make sure I'm still here, and then he go back out again.
So that's IS is equal to where omega squared is equal to, because this looks like I omega over S plus B squared plus omega squared. So omega squared is 9998.44. Yeah.
SB plus.
B is equal to 1.25. Yeah.
Yeah.
Omega is equal to the square root of 998.44, which equals. That'll do that for me, because I've got wrong numbers on my word solution now.
Uh, 31.59.
Yep. And we know that I times omega is equal to 250. Therefore, I is equal to 250.
How come you got? How did you get 31? I just put the square root.
Oh no, sorry, I've done 998.
Oh dear.
I thought I looked.
I got 99.99. Sorry.
Yeah, that's what I got.
Yeah. Sorry.
99.99.
Yeah. Dan's on form today. Okay.
250 over 99.99 equals
2.5.
Yeah, near as damn it.
That's 2.5002.
Yeah. So now we've got all the values that we need. We can say, therefore, IT is equal to A, which is 2.5, E to the minus B, which is 1.25, T, sine omega, which is 250 T.
Is that not 99.99, that one?
Oh, hang on. Yeah, 99.99. T. Yep.
Mm-hmm.
Yeah.
Okay.
Mm-hmm.
So that's how you do it.
Will that be the same? You know your graph you done on Desmos. Will that be like similar to that style?
That'll be a similar shape. Yeah.
Yeah.
That'll in fact the exponential bit, the decay has got the same time constant, both 1.25. This one's got a higher magnitude, 2.5, because you're starting off with 50 volts being applied, remember?
Yeah.
Yeah. Okay.
Yeah.
Right. If you look at the handout I've given you, the second question is back to where we started a couple of 3 weeks ago. So as a capacitor and a resistor in series with a step input of 100 volts. Use Laplace transform to determine an expression for the current during the transient period. So you need to go back in your notes a little bit, but have a go at that one.
What, I don't understand why that's different to the first one.
Because it has only a resistor and a capacitor, Callum. So this is the circuit.
But that last one was only an inductor and no capacitor. Oh no,
it
it did have
wasn't.
a
I had
capacitor. Oh no, it did. Yeah.
had an inductor with a given resistance and a capacitor, so it was RLC. This one is just 220 microfarads, yeah, in series with 4 ohms and a step
Similar to that one, Mike. It's
of 100 volts. Yeah, that wants an expression for I at T. So you need to go back and revise the very first notes and problems that we did.
Is that using Ohm's law for this one?
Yeah, Ohm's law come into all of them, Callum. Because Ohm's law is where you get the 100 over S over the other bit. Because you always start with IS is equal to VS over ZS, don't you? And that's where you get the fraction of a fraction bit.
Yeah.
In the other one, you don't get that here. But yes, you do. Yes, you do.
Yeah, that's it. Yeah.
I don't think was this what you did last week?
No, we done this back the first week. We done Laplace transforms.
Was that one of our first sessions on here? So I must have done it. I don't know.
I would think so. I couldn't possibly remember that in detail, Daniel.
Have a look.